Okay, so today we are very happy to have Ed Witten speaking to us today about his work on ensemble averaging and black hole threshold.
Okay, thank you very much for the invitation and also the introduction. So the talk is based on this paper with Jean-Marc. And let's first spend a moment or two to remember the basic idea of holographic or ADS-CFT duality. So this is the duality between an ordinary, there's a lot of noise from somewhere, by the way. Okay. This is the duality between an ordinary conformal field theory on the boundary of spacetime and a theory with gravity in the interior. The basic idea is that if you want to compute the partition function of the boundary theory on a D manifold M, here, then you sum over all manifolds X of dimension 1 more whose boundary is M. So this is a schematic picture. You specify M, you want to calculate the partition function on M, and you sum over all X's whose boundary is M. Of course, with each X, you do a path integral over metrics on X and an integral over all possible fields on X. There is a lot of background noise from somewhere.
Yeah. I'll just mute us then.
I think he's connected on the iPad and his computer, so we might be able to mute the iPad.
Oh.
We do that from here.
You think it comes from where?
I think it's coming from the iPad. It might be picking you up.
In my
Yeah.
iPad?
Try it again. I just muted you.
Okay, I thought I'd muted myself. Okay, all right. Okay, that's my, thank you. Well, I thought I was.
Local volume, which one? And it was on local volume? Can that be made higher?
Okay, this is too quiet for you.
Okay.
Are you still getting a lot of feedback, Edward?
A little bit less, but still a decent amount. Okay.
Okay, we'll keep fiddling over here.
Okay. I'll try to go ahead though. So this story works very well as long as the boundary M is connected. But it leads to a puzzle as soon as the boundary isn't connected. So what I've drawn here is a case where the boundary consists of two disjoint components, M and M prime, but X is connected. So because X is connected, it looks like an interaction between two boundary manifolds. So in one signature, we would say that there's quantum entanglement. We would have been constructing a Hilbert space, and we'd say that the quantum states are entangled. But in Euclidean signature, we're just calculating a partition function, a number, and numbers can't really be entangled. So the puzzle is, how do we interpret amplitudes associated to a connected bulk manifold with a disconnected boundary, in this case, a boundary with two components? It looks like the path integral on X is trying to calculate a connected correlation function between the partition function Z of M and Z of M prime on the two boundaries. And the trouble is that that notion, well, since the partition function is just a number, that notion doesn't seem to make any sense from any conventional point of view. So a few years ago, there was a new perspective that came from the study of JT gravity in 2 dimensions, which was a simple enough model that it could be fully analyzed. Here, the bulk is 2-dimensional, so the boundary is 1-dimensional. You'd then expect the boundary theory to be a 1-dimensional quantum field theory, that is an ordinary quantum mechanical system characterized by Hamiltonian H. The boundaries then are circles, assuming they're compact. And a metric on a circle is just characterized by the circumference beta or beta prime. So the partition function of the boundary manifold is just the trace of each of the minus beta h or minus beta prime h, the ordinary partition function in the sense of statistical mechanics. However, Saad, Schenker, and Sanford showed that JT gravity is not dual to a particular quantum mechanical system with a definite H, but to a random matrix ensemble. So they describe the ensemble. So H is drawn from an ensemble of random matrices. Averaging over an ensemble of H's means that trace e to the minus beta H is a random variable. So it has connected correlation functions. which from a bulk point of view are interpreted as the contribution of connected manifolds with disconnected boundary. In the particular case of JT gravity in 2 dimensions, this is a very nice story. It's beautifully related to famous work of the Iranian fields medalist, Maryam Mirzakhani, on the volumes of moduli spaces of Riemann surfaces. So, well, this suggested that maybe the resolution is the same in examples of the duality in 3 or more dimensions. But there's an obvious objection. No suitable ensemble of boundary theories exists. So in many much studied examples of the duality in 3 or more dimensions, essentially in all the examples constructed from string/M theory, it's believed that all parameters on which the boundary theory depends are known, and the bulk theory depends on all of the same parameters. For example, well, 2 of Modestana's original examples were ADS4 times S7 and ADS7 times S4. In each case, the only parameter is a positive integer n, and Newton's constant is an inverse power of n in those 2 examples. There are lots of examples with more than one integer parameter. Sometimes there are some real parameters. But in many cases, all parameters are known, and the bulk theory depends on the same parameters. For instance, in these examples, as I said, Newton's constant depends on n. So you could determine n by measuring Newton's constant. You could also measure n as a flux integral on the sphere, S7 or S4. So if you're a bulk physicist, you know what n is. So there's nothing that the boundary theory could be averaging over.
Edward, could we imagine averaging, say, in spectra, like averaging in time in the spectral form factor a little bit? It doesn't have to be,
you can do that
it doesn't have to be a parameter.
You can do that if you want to, but the puzzle has nothing to do with averaging over time. The puzzle exists for a definite conformal structure on M. So whatever you could say about what happens if you average over time, I want to explain what the theory is doing when you don't average over time. If you specify a particular conformal structure on M and M prime, their partition functions are just numbers. And what is gravity doing when it appears to generate a connected correlation function? So we can, you say, but we didn't have to. Now, in this talk, in the first part of the talk, I'm going to sharpen the puzzle by arguing that there's a class of observables not subject to any apparent ensemble averaging, in the sense that these particular observables only get contributions from manifolds with connected boundary. They're what we could call sub-threshold observables, where the threshold is the black hole threshold. So they're the observables that you get if you consider states that are not black holes. If you take n to infinity, or from a bulk point of view, if you take Newton's constant g to 0, keeping fixed the excitation energy above the ground state, you see a spectrum of states that has a large n limit. These states are not black hole states. And the proposal is that the energies, spins, and couplings of these states are not subject to ensemble averaging. I put the word spins in parentheses because since spins are discrete, you might consider the statement less surprising for the spins. It's more interesting for the energies and couplings of these states not being subject to ensemble averaging. So an observable that you can express just in terms of energy, spins, and couplings of these states that are not black hole states will receive contributions only from manifolds with connected boundary. Another way to describe the observables not subject to ensemble averaging is that they are the observables that can be computed by integrability. So it's not the case that all ADS-CFT examples are integrable for large n, but some of them are. In the examples that are integrable from large n, you can calculate a lot for large n, but not everything. Integrability doesn't describe the black hole physics. My claim is that precisely the observables that you can calculate by integrability are not affected by ensemble averaging. That's completely consistent with the fact that people studying integrability don't think they're studying a special case of an ensemble of theories. So the claim is that integrability, well, irrespective of what I'm saying, a fact is that integrability precisely accesses the states and couplings below the black hole threshold. And I'm claiming that those are the states and couplings not affected by ensemble averaging. So the concrete evidence for I believe the proposal is general in all dimensions. But the concrete evidence in our paper comes entirely from the three-dimensional case, and by studying classical solutions in which ADS3 is replaced by a more general hyperbolic 3-manifold X, which just means a classical solution of Einstein's equations in 3 dimensions with the appropriate conformal boundary. We'll show that hyperbolic geometry works out in such a way that sub-threshold observables only receive contributions from connected manifolds. Well, if there really is a class of observables not subject to any ensemble averaging, that strongly indicates that there isn't any ensemble averaging in examples of ADS-CFT duality derived from string/M theory. Of course, there was a good reason to believe that anyway. There's no ensemble. The fact that there's no ensemble is actually why I expected what I'm telling you would be true. To prove it, I needed help from an expert on hyperbolic 3 manifolds, which was Jean-Marc Schlenker, as I've said. Now, if there's no ensemble and there are observables not subject to ensemble averaging, you might ask why any observables are subject or appear to be subject to ensemble averaging. I'll make a proposal at the end of the talk. For now, I'll just point out that the observables subject to apparent ensemble averaging involve black hole states. So the proposal will involve the difference between black hole states and subthreshold states. It's a difference that's only sharp in the semi-classical limit where Newton's constant is small, but that's good enough because that's the limit where we do our calculations. Well, in anti-de Sitter space, there's a Hawking-Page transition. Above the transition, you see black hole states. Below them, you do not. Actually, that's another statement that's only sharp for small g or large n. But it is sharp for large g and small n. Sorry, small g and large n. So the sub-threshold observables that I claim do not see ensemble averaging are the ones that involve the states below the black hole threshold. Perhaps I should mention, since I pointed out that d equals 2 jt gravity, first of all, was exactly analyzed, and secondly, does involve an ensemble average. Perhaps I should point out that in that example, there's no black hole threshold. In fact, all states are black holes. So what I'm saying is completely consistent with what's observed in that example. That's not an example of the duality that's derived from string/M theory. So what I'm really telling you is that I think that in all examples derived from string/M theory, there's no ensemble, and there are these sub-threshold states that aren't affected by disconnected boundaries. So the next part of my talk, I'll explain what is the evidence in d equals 3, but perhaps I'll stop for a moment for questions.
So are you going to have a proposal for what the disconnected boundary amplitude is computing?
Yes,
Okay.
I'll explain. In the last part of the talk, I'll make a proposal for how to interpret what we get when we have disconnected boundaries. But
Okay.
to help motivate that proposal, it will help to know that some things are not affected by disconnected boundaries.
Sure.
So in the first part of the talk, I'll tell you what amplitudes aren't affected by disconnected boundaries, and then we'll discuss what's different about the ones that are affected by disconnected boundaries.
Okay.
Are you going to mention any speculations about what happens when you're not strictly at large n? Is there some sense in which you, I don't know, average over some small region near some particular point, or?
Well, since I claim there's no ensemble, any averaging is implicit. I'll explain at the very end how I think we should interpret it, and then we can repeat your question. Any other questions? Okay, anyway, now we're going to discuss d equals 3. So even before the general understanding of ADS-CFT duality, Brown and Hanot had discovered that in an ADS3-like universe, that means a universe that looks like ADS3 at spatial infinity, there's a boundary stress tensor, as if there's a 2D conformal field theory on the boundary of the universe. In terms of Newton's constant g and the radius of curvature L, the central charge is their formula 3L over 2G. So the semi-classical region for gravity is that G is small compared to L. So in other words, C is large. So C corresponds to what I've been calling n. And in actual examples derived from string/m theory, C usually does depend on some integers. But for our purposes today, you can just think of C as being n, the parameter that we take to be very large. Now, there's much more to a conformal field theory than just a stress tensor. But with the modern understanding, we believe that in the examples of the duality derived from string/m theory, there really is a 2D CFT with this value of C on the boundary of an asymptotically ADS3 universe. The ground state energy of a 2D CFT is minus C over 12, which with the Brown-Hanot formula for C, this one, is minus L over 8G. And the important thing about the formula is that it's, first of all, negative, and secondly, large and negative when G is small. In other words, semi-classically, the ground state energy is very large and negative. For large beta, the CFT, large beta, of course, means small temperatures, beta being the inverse temperature. For large beta, the CFT partition function trace e to the minus beta h is dominated by the ground state, so it grows exponentially as e to the beta L over 8G. That shows exponential growth for large beta with a very large coefficient if G over L is much less than 1, which is the usual semi-classical regime for gravity. Well, how do you reproduce this exponential growth in gravity? Well, I've written the Einstein-Hilbert action. I've omitted boundary terms, which, well, involve some technicalities, but turn out to only affect the normalization that I'm about to mention in 3 dimensions. So the second term is just the volume times a constant. On shell, the scalar curvature is minus 6 over L squared in 3 dimensions. So the first term is also a multiple of the volume. On shell, the action is just the volume over 8G, except I think it should have been 8G L squared. In ADS CFT, however, you're usually interested in manifolds X that have a non-empty conformal boundary, M, and such a manifold always has infinite volume. So this volume is infinite. So the counterterms are important. What you do is adjust some boundary counterterms to cancel the divergence in the volume, and then you define a finite renormalized volume. And the renormalized action, I sub r, is a multiple of the renormalized volume. So the relation between volume and action still holds after renormalization means that you subtract from the action a multiple of the area of the boundary, and that the multiple is adjusted so that the difference is finite. So the renormalized volume is finite for any given x, but it's no longer positive definite. Normally volumes are positive, but renormalized volumes are not positive because of the subtraction that's been made. So I sub r can be negative. And the fact that it can be negative will be important in the lecture. So the contribution of a manifold X to the path integral for small g is e to the minus the action, which is e to the minus the volume over 4 pi g L squared. Where I've omitted all kinds of quantum corrections, one loop determinants and higher order corrections in perturbation theory. But those do not depend exponentially on G. The exponential behavior in G for small g comes entirely from the classical action. So for small g, what we care about is the exponential dependence on G that comes entirely from the classical factor. So let's go back to the question of how to recover exponential growth from ADS CFT. Well, we have to reproduce this exponentially growing thing from the exponential of minus the renormalized volume. So we need a negative value for the renormalized volume. And that's possible because of the subtraction that went into defining the renormalized volume. But it's rather special. It only happens somewhat exceptionally, which will be the basis for what we'll say later. So to get this exponential growth, the renormalized volume has to be not just negative, but proportional to beta, so that it's large and negative for large beta. So in fact, here I've written the metric of anti-de Sitter space. Well, I wrote it in Euclidean signature. If you change the sign in front, that would be a Lorentz signature. And we don't need to take t to be a periodic variable, but if we write this metric and take t to be a periodic variable with period beta, then it describes a thermal, then the boundary is appropriate to describe a thermal partition function. And it has precisely the correct negative value of the renormalized volume to make the right contribution to the partition function. That statement is equivalent to the computation of the ADM mass of ADS3 in the original paper on the BTZ black hole. So, as shown by BTZ, ADS3 itself has a ground state energy that's very negative, and which Strominger later interpreted as this minus C over 12, or sorry, plus C over 12. No, minus C over 12, where C is given by the Brown-Hanot formula. But anyway, the ground state energy is very negative, but the black hole threshold is at energy 0. So since the black holes are at energy 0, they make contributions that don't grow exponentially. All exponentially growing contributions to the partition function come from states of negative energy. In other words, from what I'm calling subthreshold states. States above the black hole threshold have positive energy, and their propagation gives exponentially decaying factors, not growing factors. So that's going to be how we'll single out subthreshold states. They make contributions to certain things that exponentially grow when beta is large. And that's a statement that's independent of what n is. It only involves taking beta to be large, irrespective of n. So what we're going to do now is to consider observables that are entirely describable in terms of the energies and couplings and spins of subthreshold states. And then I'll argue that they only receive contributions with connected boundary. So for starters, we could consider the partition function of the boundary CFT on a genus 2 surface M. And on M, I've drawn 3 circles, A, B, and C, which are non-intersecting and also homologically independent. So when I draw the picture suggests an embedding of this surface in R3. And for that particular embedding, there's a natural X whose boundary is M, namely the interior. If you just take that picture and imagine you're seeing it embedded in R3, the interior, when it's embedded in R3, is topologically what's called a handle body or a Schottky manifold. And the picture suggests a particular handle body. It's the one in which the particular circles A, B, and C are all boundaries of disks, namely the disks you can see here. Now, what's a little bit harder to see intuitively is that there were infinitely many other ways to embed the same Riemann surface in R3, where 3 different circles would have played the roles of A, B, and C. With that other embedding, it would have suggested a different X, and some other A prime, B prime, and C prime with the boundaries of disks, but not A, B, and C. Now let's discuss what happens in the limit where the cycle A is pinched. Pinching the cycle A means that we take it to be very small. We take this distance very small, but conformally, that's the same as taking this to be large. So you either say that there's a long tube or a very narrow neck. Conformally, they're completely equivalent. What is conformally invariant is only the ratio of the length of the tube to the width of the neck. In the limit where that's large, the CFT partition function will grow exponentially due to a contribution that'll go as e to the beta times C over 12. Sorry, minus C over 12, the ground state energy. In other words, the ground state propagating through this tube, because it has negative energy, will give an exponentially growing contribution to the partition function in the limit in which beta is large. And that's, again, an exact statement independent of n. It's a universal statement about CFTs. It has nothing to do with C being large. So we're going to want to understand what kind of 3 manifolds give exponential growth when we pinch A. But it turns out that there are infinitely many 3 manifolds that will give exponentially growing contributions when we pinch A, the cycle A. So the behavior when we pinch A will be reproduced by 3 manifolds X, whose renormalized volume goes to minus infinity when A is pinched. It turns out there are infinitely many of them. But we don't expect all terms in the amplitude that have exponential growth when A is pinched to be free of ensemble averaging. If there's exponential growth when A is pinched, it means that a subthreshold state is propagating through A. But it says nothing about what's propagating through B or C, which might be black hole states. And since the amplitude partly involves black hole states, we do not expect it to be free of ensemble averaging. However, suppose that X is such that the renormalized volume goes to minus infinity when any of A, B, or C is pinched. I claim that such a contribution to the partition function, well, okay. That'll correspond to a contribution to the partition function that grows exponentially when any of these three tubes become long. So it'll be a contribution to the partition function that grows exponentially in each of three channels. That means that we'll be seeing a subthreshold state in each of the three channels. And in this situation, I claim that we will get a contribution, that an observable that doesn't see ensemble averaging. You see, in this situation, X is contributing to an amplitude with subthreshold states propagating through each of A, B, and C. Imagine taking a knife, cutting M along A, B, and C. Oh, sorry, let's go back to the picture. Take your knife and literally cut along A, B, and C. So literally just cut those circles, or take a piece of scissors. If you think of this Riemann surface as being made of something you can cut with scissors. You see, if you cut on A, you decompose it into two components, which is each a genus one surface with one boundary. But if you cut on B and on C, you get two three-hole spheres. For example, on the left, A is a hole, and then a second hole is B from above, a third hole is B from below. So when you cut on A, B, and C, you decompose your genus two surface into a union of two three-hole spheres with some gluing laws among their boundaries. So let's now look at a three-hole sphere drawn here. And I imagine labeling the external boundaries of a three-hole sphere by subthreshold states I, J, and K, and computing the partition function of the sphere with three labeled states on the boundary. By the operator state correspondence of CFT, the path integral on the three-hole sphere computes the trilinear coupling lambda ijk of the vertex operators that correspond to the three states. So when I said at the beginning that the energies and couplings of these subthreshold states are not affected by ensemble averaging, this, to be precise, is what I mean by the couplings of these subthreshold states, precisely this path integral on the three-hole sphere.
So just to be clear, so I, J, and K could be black hole states. It's just that you're working in a particular regime of the moduli space where those are highly suppressed.
Well, you could write the partition function as a sum. It's better not to express in terms of moduli. So it's a sum over all states I, J, and K going through the three cycles times lambda I, J, K squared. And then there will be an exponential of minus beta 1 lambda, well.
Right, but the betas are moduli of the surface, right?
Well, yes, but I want to fix the betas. Then instead of fixing, see, if I fix the betas, all states will contribute to the sum.
Yes.
So that isn't what we want to do. What we want to do is to work modulo. We don't literally take the whole function z of the three betas. We work modulo functions that don't grow at infinity. So we take this expansion, but we only discuss the terms that are exponentially growing in each of the three channels. So the full partition function is subject to ensemble averaging. The part of the partition, my assertion is that although the partition function is subject to ensemble averaging, the fluctuations do not grow as the three betas go to infinity. Is that statement clear, Emil? Not why it's true, but just what the statement is. So Z, okay. If it fluctuates, that means there's a z and there's also a z tilde. And I'm not claiming that z minus z tilde is 0. I'm saying that z minus z tilde has no growth at infinity.
I'm not sure there's a what's z tilde. We're working in a fixed conformal field theory, which has no boundaries at the moment, and we're just talking about. I thought the betas were just some particular values of the moduli of that Riemann surface.
I was jumping to the gravitational description. So I was trying to convey some intuition.
Okay.
So when we compute from gravity, we will get apparent ensemble averaging if we compute the full partition function z. But I'm saying that the apparent ensemble averaging never contributes a term that grows exponentially in each of the 3 channels.
Sure.
That's what the assertion is. I haven't told you the evidence for it yet.
Right. So could I rephrase it as some statement about the asymptotics of the full partition function in some corner of the moduli space?
The corners where the 3 betas are big.
Yeah.
The statement is that there are lots of exponentially growing terms in that corner. When I say exponentially growing, I mean separately exponentially growing in each of the 3 channels
Right.
in that corner. But we're only talking about the terms that are separately exponentially growing in that corner as a function to each of the 3 betas. So it's only that part of the partition function.
Right.
I'm discussing the partition function modulo terms that are not jointly exponentially growing in all 3 channels.
Mm-hmm. So I guess in the theory of modular forms, this is some statement about the cusp behaviors of modular functions or modular.
It would be like, well, this is probably much more complicated because we don't have homomorphic modular forms and they're the 3.
Yeah, sure.
But it's analogous to what you're saying. It would be like claiming that the singular terms have no ensemble averaging, although the regular terms have apparent ensemble averaging. After convincing ourselves that the singular terms do not have apparent ensemble averaging, we'll then discuss why anything appears to have ensemble averaging.
Got it.
Any other questions?
Can I ask, does this apply to sphere 4-point functions?
Well, it's a slightly tricky question, which I also was asked yesterday in another talk. Maybe it would be better to come back to it at the end.
Okay.
There are a couple somewhat slightly conflicting answers I'm tempted to give, but I think it will be a little bit confusing if I try to give them now.
Okay.
So, okay, we caught M and we got 2 3-held spheres, and the partition function of a 3-held sphere is a trilinear coupling of the 3 states. Our basic hypothesis is that the energies of and spins and couplings of states with negative energy aren't affected by ensemble averaging. So to state a prediction for hyperbolic geometry, that means if M is a genus 2 surface, and it's a component of the conformal boundary of X, and the renormalized volume of X goes to minus infinity when any of A, B, or C is pinched, then the conformal boundary of X should be connected, and thus should consist only of M. So that's the statement in conformal geometry, hyperbolic geometry, that goes with the statement that apparent ensemble averaging won't affect the part of the partition function that exponentially grows in each of the 3 channels. So, well, in a moment I'll state the genus G analog of this, but this and its genus G analog is true, first of all, and that's the evidence we have for the statement that sub-threshold observables aren't affected by ensemble averaging. So I'll just briefly say the genus G generalization. Here I've drawn the genus 3 case. You take a genus G surface, if you cut it on 3G minus 3 independent circles S alpha, it decomposes into a union of 2G minus 2 3-held spheres. And if the volume goes to minus infinity when any one of the 3G minus 3 S alphas is pinched, that means that X is contributing to a part of the partition function that blows up exponentially in each of 3G minus 3 limits. In that case, we expect the boundary of X to be connected and to consist only of M. So again, that statement is true. So the mathematical part, our paper has a section with a qualitative summary of the proofs, but it also has an appendix written by my co-author with a careful mathematical explanation of why this is true. So actually, we proved two statements. I'm a little worried about the time. Okay, we proved two statements. The first is that when a cycle is pinched, the normalized volume remains bounded if the cycle that's pinched is not the boundary of a disk in X. So M is a Riemann surface that's part of the boundary at infinity. This symbol means the boundary at infinity. So this symbol is the boundary at infinity. So M is part of the boundary at infinity of X. When you pinch a cycle gamma in the boundary, the normalized volume remains bounded if gamma is not the boundary of a disk, and goes to minus infinity if gamma is the boundary of a disk. That's one statement. So that tells us exactly when the normalized volume goes to minus infinity. Second statement is that if there are 3G minus 3 independent one cycles in M that bound disks in X, then the boundary of X is connected and consists only of M. And moreover, X is what's called a Schottky manifold. So the statements tell us, well, without the last part, the statements tell us that an amplitude in genus G that blows up in each of the 3G minus 3 channels, so we expect it can be computed just in terms of the sub-threshold observables, isn't subject to any apparent ensemble averaging. The last statement that X is a Schottky manifold is a bonus that we didn't need, but it's an interesting simplification. A Schottky manifold is just the most obvious type of 3 manifold whose boundary is a given M. So going back to this picture, as I remarked before, the picture suggests a 3 manifold with boundary M, namely the interior when M is embedded in R3 in the way that the picture suggests. And that 3 manifold is called a handle body topologically, and in hyperbolic geometry, it's called a Schottky manifold. So these statements here actually mean, taken together, in the genus 2 case, there's actually a unique 3 manifold that gives a contribution that blows up exponentially in each of the 3 channels. And that's the obvious one suggested by the picture. So there are infinitely many other 3 manifolds that contribute to the same partition function, but none of them give contributions that blow up exponentially in each of the 3 channels. So it's more than we needed, but anyway, it's true. So we learned that to the extent that a sum over classical solutions is enough, genus G sub-threshold amplitudes can be computed just by summing over Schottky manifolds. So I have a couple slides with a little bit on the proof. I don't want to spend much time on it though, because I want to explain what we say about how to interpret ensemble averaging for black holes. But just very briefly, I'll indicate the idea of the proof of one of the statements, which is that if 3G minus 3 cycles in M are boundaries of a disk, which hyperbolic geometers describe by saying that the cycles are compressible, then the boundary of X is connected and X is actually Schottky. The proof is by induction on the genus of M. And for the basic idea, let's take this particular circle here and suppose it's the boundary of the disk in X. Now, take your knife, first of all, and cut the boundary on A. And then since we're given that A is a boundary of a disk in X, and I've drawn that disk, you actually could use your knife to cut that disk. When you do that, the boundary becomes disconnected. In this example, it has 2 components, each of genus 1. And by induction in the genus, if you've already proved what we're trying to prove in lower genus, you learn with a little more thought that it's also true in genus G. So I won't say more, except that you literally cut, you're given, in the statement you're trying to prove, you're given there are a lot of cycles in the boundary that are boundaries of disks in X. So you pick one of them and cut on it, and then make an induction in the genus. The other statement that the normalized volume goes to minus infinity if and only if gamma. The other statement is that when you pinch a curve gamma and m, the normalized volume goes to minus infinity if and only if gamma bounds a disk. That's more subtle, especially the only if part. So I'm not going to explain the proof, but I'm going to give an example where you can easily check that it's true. And this example is the simplest example of what we're talking about. What we're talking about are solutions of Einstein's equations, which are connected but have disconnected boundary. There's one extremely elementary example, and it's extremely easy to check that it has the property I'll tell you in a second. And being familiar with that was actually part of the motivation for the work. I realized that if everything behaved the way this example behaves, then it would go a long way toward explaining what apparent ensemble averaging means. So therefore, that motivated trying to find out whether the behavior was typical. So for this simple example, you take your Riemann surface M of genus 2 or more, you take a metric on it of constant curvature -2, and then there's an explicit hyperbolic metric in 3 dimensions, which is just dt squared plus cos squared t times d omega squared. So that actually has 2 components of its boundary at infinity. Let's call them ML and MR. They're both copies of M. One is at t equals plus infinity, one is at t equals minus infinity. They have the same metric, so they have the same or opposite complex structures. No cycle in either ML or MR bounds a disk in X, because X topologically is just M times R. Since R is contractible, taking the product with R doesn't make anything the boundary of a disk if it wasn't already. So non-trivial cycles in ML and MR are not boundaries. So the statement that I'm not going to prove, but the more subtle of the 2 statements, where in the world is it? I think it's a mistake to scroll back this far, sorry, I won't. Anyway, the statement that we're not proving, I'm just illustrating, is that the normalized volume never goes to minus infinity. So, since no cycle bounds a disk. In fact, if you do a very short calculation of the volume of this thing, you'll see that after subtracting the appropriate multiple of the boundary area, you get a topological invariant. It certainly never goes to minus infinity. Now, this example has a drawback, which is that for this explicit metric, you can't vary independently the complex structures in ML and MR. So you don't know what happens if, say, you pinch a cycle in ML, keeping MR fixed. So there's an existence proof that more general hyperbolic metrics exist, where you can vary the 2 complex structures independently and pinch one but not the other, but no explicit formula. So one needs a better proof, which can be given by using properties of the Weil-Petersson metric and the stress tensor of the CFT. But that's all that I'll say about that proof. You can read about it in the appendix of our paper, if you wish. So the manifold M times R, like others with disconnected boundaries, only contributes to amplitudes that involve black hole states, never to amplitudes that can be expressed only in terms of energy spins and couplings of states below the black hole threshold. Anyway, that's what I have to say by way of evidence that sub-threshold amplitudes don't see any sign of ensemble averaging. So that's evidence that there's no ensemble averaging, because if there was any ensemble averaging, how would it manage to not affect a large class of observables? But this shouldn't come as a surprise because, as I've said, anyway, there's no suitable ensemble. So, well, I think what I've said is okay, I'm not sure whether what I said should have been expected or not. Since there's been a puzzle that there's no ensemble, but some things seem to behave as if there is an ensemble. Now I've sharpened the puzzle by identifying things that don't behave as if there is an ensemble. So maybe I'll stop here again for questions before I try to explain an interpretation of why anything is affected by ensemble averaging. So anyway, why do amplitudes involving black hole states show signs of ensemble averaging? Clearly, an explanation must involve a difference between subthreshold states and black hole states. I'm going to suggest that these two facts are the key differences. First, black hole physics is highly chaotic, as shown by Schenker and Stanford. Secondly, the energies and couplings of black hole states do not have a large n limit. The first point about chaos is well established, and it was part of the motivation for the work on JT gravity that led to the understanding that JT gravity is an ensemble average. The assertion that energies and couplings of black hole states don't have a large n limit might seem less obvious, but I think if you think about it for a moment and ask yourself, in what sense could you hope for them to have a large n limit? You might quickly get discouraged. The entropy, say at fixed temperature, grows as a power of n. So the Hilbert space when n is 10 to the 6 plus 1 is much bigger than the Hilbert space when n is 10 to the 6. Most states are new. In the somewhat analogous case of the large volume limit of quantum statistical mechanics, the accepted answer is that the Hilbert space does not have a large V limit, large volume limit. That's actually why the thermofield double state was introduced in rigorous approaches to quantum statistical mechanics. It does have a large V limit. Likewise, in the case of the black hole, the thermofield double entangled state of two black holes has a large n limit. But there's no reason to believe there's any unknown sense in which the black hole Hilbert space has a large n limit. So I want to underscore what I mean by the assertion. In saying the black hole energies and couplings do not have a large n limit, I mean that both in any sense I can think of and in any sense that we maybe can't think of right now. The statement is really that black hole energies and couplings have no regularity for large n beyond what's already known. What's already known? Well, what's already known is that the entropy and similar averages over the spectrum are smooth functions of the energy, spin, and n and other conserved charges, if any, like electric charge. And another thing which is known is that certain averaged functions of couplings, sorry, this should be not the sum over I, J, and K, but as initially shown by Cardy, Maloney, and Maxfield, and then later in more situations by other authors. If you take the average square coupling, averaged, for example, over a small band of energies, that's a smooth function of the energy, spins, and n. So there's a lot of stuff that we know has a smooth behavior for large n. But I'm asserting that there's no regularity for large n that we don't know about in spirit. Now, assuming this, consider any observable, curly W, that only depends on the Hamiltonian Hn of the black hole states. The most important is the partition function, but we can consider any W, and I think it's clearer to make this argument for a general W before specializing. Chaos means that as far as any simple measurement is concerned, Hn looks like a pseudo-random matrix drawn from an ensemble that's determined by the thermodynamic functions. The entropy as a function of energy, n, and other charges. If the spectrum has no regularity for large n beyond thermodynamics, this suggests that the Hn for different n are independent draws from a random matrix ensemble. Maybe I should have said independent pseudo-random draws, because of course Hn is not random at all. Hn is the Hamiltonian of a unique CFT. But chaos means that it's pseudo-random, and now I'm saying that the Hn for different n are independent pseudo-random draws from an ensemble of random matrices. There are two qualifications needed here. One, the ensemble itself depends non-trivially but smoothly on n, since the entropy is a smooth function of n, say the entropy at fixed temperature, for example, or at fixed energy. Two, as I'll explain at the end, the Hn for different n are not truly statistically independent. They only are exponentially close to being statistically independent. But, well, there is this exponential error, which might lead eventually to deviations from random matrix predictions. But in presenting this, I'm going to ignore the second point. Well, I'll ignore both points. And just, I think for first orientation, just to mention that Hn for different n are independent pseudo-random matrices. If that's true, an observable that depends only on Hn will be a smooth function of n, if and only if it's self-averaging in random matrix theory. Where something is called self-averaging in random matrix theory, if it has almost the same value for almost any draw from the random matrix ensemble. For example, the partition function is believed to be self-averaging for sufficiently small real beta. But if we give beta a sufficiently large imaginary part, it's believed to be no longer self-averaging. So there are observables that depend only on H, which are self-averaging, and there are those that are not. With presently known methods, whatever we calculate are smooth functions of n. So we can, at least whatever we calculate from, well, let me leave it at that. So we can only calculate the expectation value of W if W is self-averaging in random matrix theory. Even if W isn't self-averaging in random matrix theory, it may have a non-zero random matrix average. In that case, known methods might suffice to compute a smooth function of n that would really be only an averaged value of W averaged over nearby values of n. More generally, consider k functions W1 up to Wk that only depend on the Hamiltonian. Whether or not the Wn are individually self-averaging and whether or not they have non-zero averages, their connected correlation function may have a non-zero average in random matrix theory. If so, presently known methods might suffice to compute a smooth function of n, though with the averaged value of this correlator averaged over nearby values of n. These general considerations don't tell us how we're supposed to do the calculation. But let's specialize to the case that the W's are all partition functions for different values of the inverse temperature. Given all we know about path integrals and quantum gravity, there's an obvious hypothesis. If you want to calculate the average over nearby values of n of a product of observables, each of which is a partition function, well, a single partition function you'd compute by looking at manifolds whose boundary is a single copy of S1 times SD minus 1. Except I think it should be SD minus 2. Sorry. Where the circumference of S1 and the rth copy is beta r, and the SD minus 2 has unit radius. So if we had one partition function, then we would know the rules, and we would have one boundary with this topology. And the obvious hypothesis is that if you want to calculate an average of a product with k of them, you should look at x's whose conformal boundary is a disjoint union of k copies. So the hypothesis is that that's what we're getting when we do a calculation with a manifold with disconnected boundary. We're getting an average over nearby values of n, or a smooth approximation to a function that may actually have an irregular behavior as a function of n. The proposal is that that's the meaning of connected amplitudes with disconnected boundary for this particular case of the boundary topology. But that's a very special case. So I should generalize the hypothesis to accommodate general boundaries. Well, I started with observables that only depend on the Hamiltonian because random matrix theory is better understood than random conformal field theory. But with more general boundary manifolds, we have to talk about pseudo-random conformal field theories, not just pseudo-random matrices. What would we mean by a pseudo-random CFT? while the couplings of any states are constrained by suitable crossing relations that they satisfy. If you want to satisfy the crossing relations and all other CFT axioms exactly, then it's believed that there's no appropriate ensemble from which they can be drawn. That was the original puzzle. There's no ensemble of CFTs that we could be averaging over. But if we're just discussing asymptotic expansions for large n that we get from the gravitational path integral, it's plausible that there's a large ensemble of asymptotic solutions of the crossing relations. That would be analogous to the following. So unitary and physically sensible relativistic S matrices are presumably scarce, but in low energy effective field theory, there's a vast swampland, parameterized by the coefficients of all possible operators in the effective action of relativistic S matrices that make sense to all orders in a low energy expansion. Thus, the proposal would be that the CFT that governs black hole states for particular values of n looks like a pseudo-random draw from a vast swampland of effective CFTs that satisfy all crossing relations in an asymptotic sense for large n, but not exactly. So the CFT for n of 1,000,001 is a definite CFT, but if you only have access to asymptotic expansions in n, it looks like a pseudo-random draw from a vast swampland of effective CFTs that exist asymptotically, but not exactly. For nearby but different values of n, we get almost independent pseudo-random CFTs. So observables that are sensitive to the details of the black hole spectrum are smooth functions of n only to the extent that there are self-averaging functions in random, self-averaging quantities in random CFT. That means that, what is supposed to be self-averaging in random CFT? Well, the things people have learned how to calculate. So for example, well, as I mentioned, Carty, Maxfield, and Maloney had nice formulas for the averages of lambda ijk squared, extended a lot by later authors. So that quantity is self-averaging in random CFT. Anything that can be expressed in terms of anything that's self-averaging in random CFT is what you might be able to calculate from the gravitational path integral with known methods. And it will give you smooth functions of n that are self-averaging in random CFT.
Edward, when you're talking about random CFT, you're imagining solving crossing approximately for which class of operators?
All operators. Well, okay, sorry. You don't know exactly what the operators are, right? So first we had a Hamiltonian, which is pseudo-random. So it's characterized by the entropy as a function of energy. So first we had a pseudo-random Hamiltonian with that property. Then there are crossing relations, which crossing relations will be satisfied on the average, which means that all averages of crossing relations that have averages will be satisfied. So the beginning is that, okay, lambda ijk itself doesn't have an average.
But what about the labels ijk themselves? Where are they drawn from?
Well, you picked a pseudo-random Hamiltonian Hn, and ij and k are eigenvectors of the pseudo-random Hamiltonian. So what the labels are drawn from is part of what you drew. If we're discussing the swampland, in the swampland, we have the entropy as a function of the energy. That tells us in a statistical sense what the labels are. You draw your Hn from the ensemble with the appropriate entropy as a function of energy. And you also satisfy relations for ijk. However, I'd like to turn it around a little bit. What will actually happen is that suppose you calculate something, maybe a single boundary, maybe multiple boundaries. You could express what you're calculating in terms of sums over states and products of couplings ij and k, lambda ijk in different channels. Then you get a big product of of a sum over labels is the product of a lot of lambdas. It might or might not be self-averaging. Or at least, even if it's not self-averaging, it might have not, it may have an average. And look at the paper of, well, I apologize to not have all the references handy, but look at the paper of Cardy, Meroff, and Maxfield, and the later papers where it's shown how to describe various averages. If you can compute what you want in terms of their averages, that'll be the type of quantity that's self-averaging in random CFT. What I'm saying is kind of a tautology, to be honest with you. I'm not saying much, except I'm just reformulating what people have already said in a way that tries to show that it's actually adequate to explain the puzzle. I'm not sure.
Ask a related question.
Yes, go ahead.
So is your proposal somehow that this definition of an average, should I worry that I don't really have a measure in N on how you say it's like a pseudo-random draw from a ensemble at large N, a pseudo-random Hamiltonian. Do I just do this? What is the average? What is the quantity that computes these smooth functions? Do I need to worry about a measure or no?
Well, it's a tautology. You should ask the following question. Okay, I told you what ensemble you do the energy level thing. That was from knowing the entropy as a function of thermodynamic variables. You could have asked me for what ensemble would you draw lambda ijk. Well, I'm going to give an answer that will show it's kind of a tautology. You calculate lambda ijk squared from the type of calculation people have done, and then there are other products of lambdas that have averages. Not everything that has an average has been analyzed in the literature, but various things have been. The ensemble is characterized by whatever the averages are that you infer. So people have written a variety of papers inferring statistical properties of averages of couplings. And those results characterize the ensemble. So the people have usually done that for pure gravity, but it has to be done for the theory you're actually interested in, not for pure gravity. So if you have a particular model of ABS-CFT duality, you'd run the story that people have run to find averages of lambda ijk squared and so on, that you infer from the gravitational path integral, basically. They didn't get it out of magic. They got it, well, in the literature, it's mostly done by sort of looking at CFT abstractly. But when you have a gravitational dual, you would use the gravitational dual and you'd be able to get more information about these averages than you can get abstractly. And the gravitational path integral would tell you what the ensemble is. And then all I'm telling you is that whatever that ensemble is, for a given large integer n, you're looking at a pseudo-random draw from that ensemble.
So you can turn this around. So these quantities that people have computed in the literature is typically some Cardy style derivation of these averages. And you're saying, well, I can turn this around and say that this is telling you something about the statistics of large N CFDs in N itself.
Yes, that's true, but yes, people do Cardy style because, as I said, it's okay. Most of the papers give results that are, I'm not sure I know the complete literature properly, and there can be gaps in what I'm saying. Most of the papers, though, give results that are valid for an arbitrary CFT, but you can expect to get sharper results for a holographic CFT because you know more. See, you know more about the genus 2 partition function, for example. Well, to the extent that it can be calculated from the gravitational path integral. You know more about it than you know about an abstract CFT. So the statements that are made in literature are not as strong as you'd be able to get if you use properties of the gravitational path integral. If you study the gravitational path integral, you would get results that you interpreted as giving various averages of couplings. And all I'm saying is that you should think of the theory for n, for given very large n, as being a pseudo-random draw from an ensemble that's characterized by whatever you would have learned that way. It's kind of a tautology, but I think it would perhaps make one feel better about what one understood.
Understood.
So as I've said, we can only compute quantities that have non-zero averages in random CFT. And what we compute are smooth functions of n that are smooth approximations to the observables of interest. So going back to the original question, where we compute the expectation value of a product of partition functions, the connected correlator, by summing over connected manifolds with disconnected boundary, what we're getting is a smooth function of n that's really an averaged value of the product in question, averaged over nearby values of n. A short summary is ensemble averaging is really averaging over nearby values of n to get a smooth function of n. But it's important that we didn't do the averaging on purpose. It happened because we only knew how to do asymptotic expansions, and the asymptotic expansion automatically produced this smooth function. There's one statement I still want to explain, which is that the theories with different but nearby values of n are only exponentially close to being statistically independent rather than being truly statistically independent. That's because in known examples, the theories with different n are unified in string/m theory and are connected by domain laws. Here's a picture. So again, I have the manifold X that's connected with disconnected boundary. And we've wrapped a brane that causes a jump in n between two boundary components. So there's one value of n here, and it's n plus 1 over here. This will compute a connected correlation function between partition functions with different values of n. Since there is such a connected correlation function, that means the theories of different n are not truly independent. But the connected correlators are exponentially small because of the brane action. In other words, the action for this brane contributes to the connected correlator, but wouldn't contribute to the disconnected correlator. So there are exponentially small deviations from this statement that we're dealing with random CFTs for different values of n. And it's conceivable that eventually one would see that there actually are exponentially small deviations from random matrix theory in the gravitational path integral. So the subject we're discussing today started a few years ago with observations that the gravitational path integral gives results similar to what you get from random matrix theory if we ask certain questions. But here I'm suggesting at the end that a more careful examination might show exponentially small departures from random matrix theory. To summarize, today I've given evidence that energies and couplings of states below the black hole threshold are not affected by ensemble averaging, and I've proposed an interpretation of apparent ensemble averaging in the case of black holes. Thank you.
So would an example of this sort of ensemble averaging, so I'm thinking about ADS3 in string theory with NS fluxes, then we know that the worldsheet theory for that works at fixed Lagrange multiplier for the fundamental string charge rather than fixed fundamental string number in the background. So is that an example of the sort of averaging over n that you would be thinking of? In other words, more generally, you know, if we worked at some kind of fixed chemical potential for n, is that the sort of thing you have in mind? Go to some Legendre transform with respect to n?
I think I have to say no, because I'm not suggesting that we should average with respect to n. I'm saying that the theory is well defined for given n.
Sure.
And the question is why it appears, even though the theory, it appears that no ensemble is necessary, yet it appears when we do calculations that we get ensembles that look like we get answers that look like they came from an ensemble average. That's the puzzle I'm trying to explain. If we voluntarily start averaging over n, we won't explain that. The trick is to explain why, when we try to calculate a definite n, we get answers that actually are appropriate, actually look as if there was an average taken over n. The answer is twofold. One is, the answer is simply, let me restate the explanation I gave. The things we know how to calculate were self-averaging in random matrix theory, just because otherwise we don't know how to calculate it. well, maybe that needed a better explanation than I've given. But if something is self-averaging in random matrix theory, that means up to exponentially small corrections, it doesn't matter whether we average over it. So the things we know how to calculate tend to be the things that look like they've been averaged, even if they weren't. So it's not that we should be doing an average to explain our calculations. It's that the theory spontaneously produces an average. Sorry, spontaneously produces what looks like an average. If we could do exact calculations, we wouldn't see an average for anything. But the asymptotic calculations we do don't know the difference between the exact CFT we're studying and a pseudo-random CFT.
Right, but you haven't, I mean, if you say what averaged quantity is being computed, then presumably you have in mind some ensemble.
No, okay. You're asking me how to interpret the computations we do. What
Yeah.
are they giving? What, as I said here, what we're getting is an average value of what we're trying to get, average over nearby values of n. A weakness of this description is that I can't tell you exactly how it was averaged over nearby values of n. I'd like to be able to, but I don't have a canonical suggestion of what the theory is doing when we do the gravitational path integral.
Okay. I think that was what I was asking. And making a suggestion that at least in one particular case, we sort of know an example of how to average over n, which is to introduce a chemical potential for n.
But we had the freedom to vary it, right? The chemical potential.
Yes.
And here, whatever is happening isn't under our control. The gravitational path integral just produces something.
Mm-hmm.
So it looks like gravity has a preferred way to produce a smooth function. So we're trying to calculate functions that have, in general, very erratic dependence on n, as was illustrated in some work by Sadchenko and Sanford, not in one of the papers I cited, but one of the other papers. And although certain observables have large dependence on n, somehow the theory produces what it regards as the best smooth approximation. But I don't know how to characterize the best smooth approximation. So in my eyes, that's the main weakness of what I'm saying. Otherwise, I think what I'm saying is sort of perhaps doesn't explain very much, but it's, I think, almost an inevitable interpretation of the known facts.
Okay.
So if I understood correctly, you're saying the quantities that you compute, if they take contributions from states with positive energy, will exhibit averaging behavior. Is that correct?
If
By
you
positive, is that energy
calculate a
input?
contribution to the partition function that's, so for example, we have the partition function that depends on the 3 betas. And the asymptotic limit up here when they're all equal to infinity. If you expand near that point, what you'll see in that expansion won't show any ensemble averaging. But if you compute any place else, you'll see ensemble averaging. So to give the, don't remember if you were the one who asked about the 4-point function in the sphere. But whether yes or not, let me make a few remarks about it. You could put 3 points at 0, 1, infinity, and the 4th point at x. And then you could expand around x equals 0. So all orders in expansion and powers of x, you will not see black holes. And you will not see ensemble averaging. But as far as I know, the exact function might see ensemble averaging.
I would expect at certain values of x, the contributions of these heavy states will be very important, the same way for imaginary betas.
Well, maybe, but there's a problem that bothers me about it. It's because of what I'm about to tell you that I didn't want to answer the question during the seminar. So let's try to calculate the 4-point function in genus 0. But I want to take 4 light operators. So there are 4 operators that correspond to subthreshold states. So there's actually no classical solution that contributes other than ADS3 itself. So if we want to discuss that seriously, we have to talk about non-solutions. And let me tell you a little bit about non-solutions. So there are known examples that are better understood than what we were about to get to, where it's believed that a non-solution is important. That's the spectral form factor studied by Saad, Schenker, and Sanford. It's basically the 2-point function of the partition function with complex conjugate values of beta and beta prime. Not real, but complex conjugate. And it's believed it gets a contribution. Well, first of all, to get a connected contribution, we need to have a geometry with 2 boundaries, which are each copies of T2. So the boundary is the disjoint union of 2 copies of T2. There's actually no classical solution. That's a rather elementary fact about hyperbolic geometry. Nevertheless, it is believed that there's a parent ensemble averaging for the partition function. The way it's believed to work is that there's a non-classical solution. We might just call it a non-solution. And in this case, it was studied in 2 dimensions by Saad, Schenker, and Sanford, but in 3 dimensions by Cutler and Jensen. So they consider the topology T2 times R. There's no classical solution, but they tried to do the path integral anyway. And they got an answer which I think has a good chance of being at least qualitatively correct. I don't know if it's the exact answer for the path integral, but they got a at least somewhat reasonable answer. The answer they proposed is completely consistent with what I've been telling you. It doesn't come from a classical solution, but it also doesn't have any contributions that exponentially grow in the limit where we don't want to see exponential growth. So this non-solution contributed to the spectral form factor, but its contribution in the limit where the 2 betas go to infinity, it didn't make any contribution. And it didn't make any contribution even when 1 beta went to infinity. When I say not any contribution, I mean not any exponentially growing contribution. So in that calculation, although it was a non-solution, it behaves in a way that's completely consistent with what I've claimed in this lecture. Now, that's the only non-solution that's been investigated in the literature. I can't promise what other non-solutions would do. I can only give that example to illustrate the fact that although the precise result I told you is limited to solutions, at least in that one interesting example in the literature, the behavior is the same when you get away from a solution. Now, unfortunately, if we go back to the 4-point function at genus 0, first of all, there's no solution. And secondly, there's also no analog of the Cutler-Jensen proposal for what to do instead. There's actually a problem about it that bothers me, which is that if you have any non-solution, no matter what it is, I don't care if the boundary is connected or not. All I care about is that a conformal transformation of the boundary, that the boundary isn't, the bulk is not ADS3, which means that a conformal transformation of the boundary doesn't extend over the bulk. That means automatically there are moduli. Let's do the 3-point function because it's easier to explain. Automatically there are moduli that come by making an SL2C transformation on the boundary that doesn't extend over the bulk. Although you could describe it in a different language where you keep the boundary fixed and change the bulk. But anyway, you automatically get some moduli parameterized by SL2C. And it's therefore easy to see that any contribution other than ADS3 itself is 0 or infinity. So I don't know how to discuss contributions from non-solutions to the 3-point function, let alone the 4-point function, to get a sensible answer. However, if it is possible to do that, then I at least would say that to all orders in an expansion near x equals 0, you won't see any sign of ensemble averaging. That's what we would really claim from my thesis in the lecture. By the way, the reason I say to all orders is that C over 12 is going to infinity. So I presented the lecture as if there was a threshold below which you're not a black hole. But in the limit where it's sharp, C is going to infinity. So the threshold goes off to infinity. So therefore, as I said, to all orders in the expansion in powers of x near x equals 0, you won't see ensemble averaging. If you do see ensemble averaging, it will be in exponentially small terms.
Yeah, it
Exponentially
was
small.
those exponentially small terms that I was when I was
Exponentially
talking.
small x, not just a number. Sorry, I can't hear you.
I was saying that it was the exponentially small terms that I was worried about in the regimes where the kinematics are such that they become important. But you're
You mean
saying in that,
exponentially small in n or in x?
well, when x would have to become comparable to n in order for those terms to start significantly contributing to the 4-point function.
Well, x can't be bigger than 1, or at least it's not useful for x to be bigger than 1. The biggest x can usually be is a half or 2 or something like that. Because if you make x large, it's just you should just expand in a different limit. So the worst you can do is to take x to be of order 1. Let's say x equals -1 or 1/2 or something. I do have this perplexity about that I told you that I don't know how to get a sensible answer from non-solutions. But leaving that aside, I don't have any prediction to make, except that to all orders in an expansion near x equals 0, you won't see ensemble averaging. Are there any other questions?
I have one question.
Yes.
We had a nice talk by Scott Collier last week, and I was wondering if you might have any comments on relation to their work, because there didn't seem to really be a role for this black hole threshold.
Well, first of all, he was discussing a variable. He was averaging, right? He was discussing an averaged observable, which is, sorry, I heard him give a talk a few weeks ago, and I'm assuming it was roughly the same talk.
Probably.
If that hypothesis is correct, then in the talk we heard, he was discussing an averaged observable, average over the coupling constant, not over n. So he wasn't trying to work in a definite theory. I have no, if you can say something interesting about an observable people haven't studied before, whether it's averaged or not, that's great. So he wasn't trying to address the question I've been trying to address today, which is what observables are subject to apparent ensemble averaging and why. He was rather averaging, studying an observable that actually was averaged.
Well, I think they made the claim that the supergravity limit of any correlation function produces the average over tau.
Yes, that was true because tau was large in the limit he was taking. Tau is, okay. When I heard this talk, I thought I understood the right way. I might make a mistake now. Anyway, I think we're getting a little bit far afield from my talk, not just to make long statements. If I can. There's one more thing I would like to tell you, which I think might be clarifying. I think there's a problem with the notion of black hole microstate, except for BPS states. For BPS states, there's a perfectly sharp notion of black hole microstate. Otherwise, there isn't, for the following reason. To say that a state is a black hole is only precise when you have a classical picture of the causality. And that's true at n equals infinity and in an asymptotic expansion near n equals infinity. To say that you have microstates is true at any definite n. At every definite n, there are microstates. But because of what I used in the latter part of my lecture, the fact that the black hole spectrum has no regularity for large n. If you take n to be infinite, or do an asymptotic expansion near infinite n, then you don't have microstates anymore. So you don't simultaneously have black hole microstates and classical causality. Sorry, you don't simultaneously have black holes, which require classical causality, and quantum microstates, except in the case of BPS states. So, I think that statement is tied up with the way I interpreted apparent ensemble averaging. Because remember, the basic assertion was that in contrast to the thermofield double, which does have a large n limit, the single-sided black hole has no large n limit and no large n regularity beyond what we already know, which are only the thermodynamic properties. Thermodynamics broadly understood to include this kind of thing. Okay.
So what does your work imply about what people typically call the factorization problem?
I've told you what I think the factorization problem means. It means that the gravitational path integral is producing smooth functions that interpolate between exact answers that are not smooth. So this was meant to be the answer to the factorization problem. So what the factorization problem is, question is how do you interpret amplitudes with disconnected boundary? So here I stated my interpretation.
I guess what I was driving at was, so yes, for the theory at fixed n, there is no such connected contribution. So, and what you're saying is that the gravity answer looks like it is doing some kind of average over some range of n's. So, so is it that we just shouldn't try to use gravity to compute these sorts of quantities, or what?
Well, first of all, what we compute here is meaningful. It's the average over, it's the pseudo-random CFT answer is what we're getting from gravity.
Mm-hmm.
So I think your question is, how would we get a better answer?
Yeah.
I don't know. In some special cases, we can get better answers, but we can get exact answers for fixed n by localization. It would be marvelous if there are cases where localization gives an answer that depends erratically on n. I doubt it happens, but I'm not totally sure it can't.
Mm-hmm.
I think it won't be, the reason I doubt it, large n integrability definitely doesn't, large n integrability doesn't tell us about black holes. It tells us only about subthreshold states and their couplings. And I think, well, okay, people have sometimes gotten, people have gotten large n exact answers for counting of BPS states in some theories. So that's an example where they did something much better than a conventional semi-constant gravity calculation. For example, Murthy et al. Sorry, perhaps to be confused about the reference, summed over infinitely many geometries and got integers. So that was exact answers. Okay. Anyway, I don't have anything new to tell you about how to do calculations, how to do exact calculations.
Are there any more questions? Well, if not, let's thank the speaker one more time.
Thanks for the invitation and the discussion. Stay safe, everybody.